Students, today we are going to start the new topic in the fourth unit, that is balancing of reciprocating masses. So in the previous class we discussed about the balancing of rotating masses for same plane and different planes. So in the continuity of that, now we are solving the methods for balancing of reciprocating masses. Then in this topic, what is the inertia effect of crank and connecting rod and single cylinder engine and balancing in multi-cylinder inline engines and primary and secondary forces and V-type engines and radial engines. Okay, these are the main contents we are going to discuss in this section of balancing of reciprocating masses. So this is the reciprocating engine. That means here we are considering a steam engine works. So mainly, what are the components available in the reciprocating engine? That is valve rod, slide valve, and high pressure steam in, and exhaust steam, crosshead head, and piston rod and the piston. So these are the main cylinder. These are the main components available in the in any engine. That is especially here the steam engine working. So why we are going to start up with reciprocating masses to be balanced? We know that the various forces acting on the reciprocating parts of an engine, the result of all the forces which are acting on the body of the engine due to the inertia forces only is known as unbalanced force. So due to that, without balancing, we will get a vibration that is called a shaking force. Thus, if the resultant of all the forces due to the inertia is to be zero, then there will be no unbalanced force. But even then, there is an unbalanced couple or shaking couple will be there. So actually, this is a schematic line diagram of a reciprocating engine. Here we are considering a piston P with a cylinder outlining. This is the crank which is rotating in the direction of clockwise with angular speed, that is omega, and the CP, that is the connecting rod which are of length L, and the distance between the center of the crank and the piston center, that is of length X. So mainly these balancing of reciprocating masses for the various inertia forces is to be balanced. For that, we are considering a horizontal reciprocating engine mechanism. The figure will show the diagram, line diagram, where Fr, that is the force required to accelerate the reciprocating parts, and Fi, inertia force due to the reciprocating parts, Fn be the force on the sides of the cylinder walls or normal force which are acting on the crosshead guides, and Fb be the force acting on the crankshaft bearing or main bearing. Since these inertia force and reciprocating acceleration force are equal in magnitude but they are in opposite direction. So if you see in the diagram, there also the Fi is towards the left hand side from the piston and Fr be the right hand side from the piston. So these are all equally but opposite direction. So So the horizontal component of Fb, that is Fbh, which is acting along the line of reciprocating, is equivalent to the opposite to the Fi, that is inertia force. And this force Fbh equal to Fu, that is unbalanced force or shaking force, and which is to be required properly balanced. And the forces on the sides of the cylindrical walls Fn and vertical component Fb, that is Fby, are equal and opposite, and thus for shaking force of magnitude Fn into x, that is the distance, or Fbv into x. From the above, we can see that the effect of reciprocating parts is to be produce a shaking force, and then a shaking couple will be arised. Since these shaking force and shaking couple are vary in magnitude and direction due to the engine cycle, and therefore they causes very objectionable vibrations. Thus, for the purpose of balancing the reciprocating masses, it is to be eliminated, and shaking force and shaking couple. In movement of the mechanism, we can reduce the shaking force and the shaking couple by adding the appropriate balancing masses, but it is usually not practical to eliminate the vibrations completely. In other words, the reciprocating masses are only partially balanced. What is the procedure here we are having in the method of balancing the rotating masses? Also, we applied the analytical and graphical method there. Here also, by applying the analytical method, we are going to unbalance what are the available couples and forces. So analytical method for velocity and acceleration of the piston. Consider the motion of the crank and connecting rod of a reciprocating engine, which is shown in the figure. And let OC be the crank and PC be the connecting rod. We all of you know that in the reciprocating engine. Let the crank rotates with angular velocity omega radians per second, and the crank turns through an angle of theta from the inner dead center. So when it is moved to a certain angle theta with a angle of theta to a radius of velocity, that is omega, let x be the displacement of the original position of the reciprocating body, that is piston, from internal inner dead center after t seconds, during which the crank angle has turned to an angle theta. So whenever here, if you see, whenever the crank position is turned to a theta angle, the piston of movement is also moved to a distance x for the limited period t. So that is the representation here. Let L be the length of the connecting rod between the centers, and R be the radius of the crank or crank pin circle, and pi be the inclination of the connecting rod to the line of stroke, and n be the ratio of the length of the connecting rod to the radius of the crank, that is L by R, that is called n. From the figure, we are going to get the velocity of the piston. From the geometry of the figure, we can see that x is equals to p dash equal to, what is the value of x means, op dash minus op, that is the gap. We can write it another one. So op dash can be written as p dash c dash plus c dash o minus op dash can be write it as pq plus qo. Then p dash c dash, p dash c dash is known as l plus o dash c dash, that is write it as the radius of the crank. So r minus pq. pq, let us consider pq as a p c dash q as a right angle triangle. From that, pq is equals to l cos pi plus qo as r cos theta. By simplifying this equation, r will be comes to common 1 minus cos theta plus l into 1 minus cos theta cos pi, that is equals to r of, by commonly taking off r from all these, 1 minus cos theta plus l by r. What is meant by l by r? That is the n into 1 minus cos pi. From the triangles CPQ and CQO, CQ is equals to L sin pi, that is equals to R sin theta, or L by R is equals to sin theta by sin pi. And L by R, will call it as n is equals to sin theta by sin pi, or sin pi is equals to sin theta by n. We know that the reciprocating masses, the unbalanced primary forces and secondary forces, the equation is cos pi minus 1 minus sin squared pi whole square minus square root of 1 minus sin square theta by n square. So expanding these equation, we get it finally 1 minus cos pi minus sin square theta by 2 n square. So substitute the 1 minus cos pi there. With that, x is equals to r into 1 minus cos theta plus n into sin square theta by 2n square equal to r into n gets cancelled, 1 minus cos theta plus sin square theta by 2n. This is the equation number 4. By differentiating the equation number 4 with respect to theta, dx by d theta is equals to r into sin theta plus 1 by 2n into 2 sin theta cos theta equal to r sin theta plus 2 gets cancelled, sin, or otherwise sin 2 theta by 2n. Then velocity of p with respect to o, or velocity of the piston, is vp is equals to dx by dt. So simply dx by dt not be getting directly, so dx by d theta into d theta by d theta by dt, we write it as omega. So omega into dx by dt as r omega into sin theta plus sin 2 theta by 2n. And what about the acceleration? Since the acceleration is the rate of change of velocity, therefore acceleration of the piston is ap is equals to differentiate the velocity. So dvp by dt. Here also the same procedure. We can't do the directly. So dvp by d theta into d theta by dt. So again one more omega is comes to the picture. dvp by d theta equal to omega r into cos theta plus cos 2 theta into 2 by 2n. So finally omega r into cos theta plus cos 2 theta by n. So multiply with omega for acceleration. So AP is equals to, already omega is there, and now by substituting the dvp value, that means rate of change of velocity value, so omega square r into cos theta plus cos 2 theta by n. This is the seventh equation. When there is a, this is the final equation for acceleration, and previously we get it the for velocity. Velocity means omega r into sin theta plus sin 2 theta by 2n. Acceleration means cos theta plus cos 2 theta by n. Only the difference is that the denominator 2n, but here denominator is n and the 2 is goes to the omega superscript, that is omega square. Now take a note of that is, when the crank is at the IDC, inner dead center, then the theta is at 0 degrees. So AP is cos theta is 0. Cos theta 0. So cos 0 will go for 1. So AP is equals to omega square r into 1 plus 1 by n. When the crank is at outer dead center, that is theta is 180 degrees, then the position is cos 180 degrees is minus 1. So minus 1 into cos 2 theta. Cos 2 into 180, that is 360. That is again comes to 0. So cos 0 is 1 by n. So omega square r into minus 1 plus 1 by n. But as the direction of the motion is reversed at the ODC, out dead center, therefore the changing the sign of the above expression. So omega square r into 1 minus 1 by n. Now calculate the primary and secondary forces. Primary and secondary forces of unbalanced force. Consider the same, the reciprocating mechanism, and the mass of the reciprocating parts as m. L is the length of the connecting rod and r is the radius of the crank OC, and theta is the angle of inclination of the crank with the line of stroke, that is PO. Omega is the angular speed of the crank, and n is the ratio of the length of the connecting rod to the radius of the crank, that is L by R. We already know the value of acceleration, that is AR is equals to omega square r into cos theta plus cos 2 theta by n. The inertia force due to the reciprocating parts is F R, or otherwise Fi, inertia force Fi is equals to mass into acceleration. So inertia force, acceleration we know, multiply with mass, m omega square r into cos theta plus cos 2 theta by n. In the previous article, we are calculated the horizontal components and vertical components. So the horizontal components of force exerted by the crankshaft bearing, that is FBH, is equal and opposite to inertia force, that is Fi. So this force is an unbalanced force which is donated by Fu. So horizontally it is opposite. So F inertia force Fi is equals to Fu, that is m omega square r into cos theta plus cos 2 theta by n. Then expand this equation, that is m omega square r cos theta plus m omega square r cos 2 theta by n. By writing these as two terms, then the expressions will be called it as primary and secondary unbalanced forces. So which is the primary unbalanced force means m omega square r cos theta is the primary unbalanced force and m omega square r cos 2 theta by n is called secondary unbalanced force. This is the formula we need to remember while solving the problems also. Directly we can substitute this in the problem. Then the primary unbalanced force, that is the formula is m omega square r cos theta. So that is to be maximum when theta is equals to 0 or 180. So substitute the value theta is equals to 180 cos 0 1 cos 0 1. So m omega square r into cos 0 1. So m omega square r. Thus the primary force is maximum twice in one revolution of the crank, and the maximum primary unbalanced force is given by Fp is equals to m omega square r. Then what about the secondary unbalanced force is maximum? The unbalanced force of secondary is maximum when theta is equals to 0, 90, 180, 360. Since it is the value we multiplied with 2, the cos 2 theta by n. So multiplication of with 2, 0 into 2, 0, and 2 into 90, 180, 180 into 2, 360. So that is the same thing we need to apply here. Thus the secondary force is maximum 4 times in one revolution of the crank without placing of any value in the theta. It is twice. Here cos 2 theta. So again it was multiplied by 2. So now it is the term called 4 times. So 4 times in one revolution of the crank, the maximum secondary force is given by Fs max is equals to m omega square r by n. From this, the secondary unbalanced force is 1 by n times of the primary force. Okay. If you categorize these m omega square r into 1 by n. M omega square r means Fp max, that is primary force maximum. So 1 by n terms of maximum primary unbalanced force. In case of moderate speeds, the secondary unbalanced force is so small that is may be neglected as compared with the primary unbalanced force. The unbalanced force due to reciprocating masses varies in magnitude but constant in direction, while due to the revolving masses and unbalanced force is constant in the magnitude but varies in the direction. And partial unbalanced primary force. Partial unbalanced, that is, the primary unbalanced force can be considered as a component of the centrifugal force produced by the rotating of mass m, which is placed at the crank of radius r. When we see in the diagram, the primary force acting from O to P along the line of stroke, which is represented in the pink color, though hence the balancing of primary force is considered as equivalent to the balancing mass m, which is rotating at the crank radius r, is given by m omega square r cos theta. That is the actual formula we found for the primary unbalanced force in the previous session. This balanced by having a mass b at the radius of b which is placed diagonally opposite to the crank. So with that, the centrifugal force due to the B, mass B, that is m omega square r, will be called it as, there the m means mass. Here what is the m? Mass is called as a capital B, and omega square, what is the radius? There it is, for mass m, the radius of rotation is r. Here for B mass, which is opposite to the mass of m, the radius is small b. So yeah, B, capital B, omega square B. Then the horizontal component of this force, which is acting in the opposite direction of primary balanced force, is B omega square B into cos theta. Then the primary force is balanced if cos theta is 0, or B omega square B cos theta is equals to m omega square r. Simply BB is equals to mr. Now the opposite force unbalanced is balanced by the mass BB. A little consideration will show that the primary balanced force is completely balanced if BB is equals to mr, but the centrifugal force produced due to the revolving mass capital B, which is having also vertical component which is perpendicular to the line of stroke of magnitude, this force may not be balanced. So the maximum value of this force is equal to B omega square B when theta is equals to 90 to 70. By substituting these values, which is maybe equal to the maximum value of primary force m omega square r is m b omega square b sin theta, since it is a vertical component, so that is y component, so that is a b omega square b sin theta. So with that, we have studied about the primary forces and secondary forces in any reciprocating parts of an engine. So actually the formula mainly here we are using for primary balanced force is m omega square r cos theta, and secondary forces is m omega square r cos 2 theta by n. This is the mainly formula. And when the primary force will be maximum means theta, for when the primary force is maximum means theta 180 360, since the value is m omega square r. And when the secondary force will be maximum means m omega square r cos 2 theta by n, so that the theta is 0, 90, 180, 360 also will be applicable here. And also finally the secondary force is the 1 by n times of the primary force. So we can reduce or we can negligible the secondary force which is of nominal, due to that there is a primary force is the maximum entity we need to find out. So with that the session is completed. In the next class we will solve the remaining methods for solving these reciprocating masses to be balanced.